Good morning. I'd like to solve today an example of solving a first order RLRC circuit that has a switch involved in it. So let me first present to you the circuit that we're going to consider today. We're going to have a multi-position switch, which allows us to connect to a source circuit that consists of a 400 volt power supply through a 100 k ohm resistor, or alternatively simply connects to a regular 50 k ohm resistor, allowing the capacitor to discharge as opposed to being charged. The capacitor has a value of 0.1 microfarad, and what we're interested in doing is looking at how the capacitor voltage and the capacitor current change during the course of time as the switch moves to different positions. So the movement of the switch is going to be as follows. At time t equals 0, the switch is going to move from its position at A to position B. This will allow the capacitor to be a charge. We're assuming that there's no initial charge on the capacitor in this problem. So once it moves to position B, the capacitor will start charging due to the connection to the 400 volt supply. And after 15 milliseconds, so when t is 15 milliseconds, the switch though is going to move from position B to position C. And this will allow the capacitor to then discharge through the 50 k ohm resistor. And again, what we'd like to do is plot what the voltage and the current of the capacitor is doing over this entire timeline. So to start thinking about the problem, let's first start at the very, very beginning. Let's look at what the initial values of the voltage and current would be before any switching. So let's look at t equals 0 minus. The capacitor has no initial charge. Therefore, the value of the voltage, the capacitor voltage at t equals 0 minus should be equal to 0 volts, and the value of the current at 0 minus should also be equal to 0 amps. What happens when we incur our first switch at time t equals 0? To think about what happens, let's draw what the circuit looks like at time t equals 0 plus, immediately after the switch changes its position. We now have a circuit where the 400 volt supply is connected through the 100 k resistor to the capacitor. I'm not drawing the 50 k ohm resistor because it's in an open circuit and therefore it's not going to affect the behavior of the capacitor. So the voltage across the capacitor is going to be labeled V of 0 plus because we're looking at the instantaneous behavior right after the switch. And there's going to also be some current going through, which is also IC of 0 plus. Now the key principle that we use when thinking about initial conditions is what I call the continuity principle. It's the idea that in capacitors, the voltage cannot change instantaneously, and in inductors, the current cannot change instantaneously. You can remember which one it is by just remembering what the elemental equation is for your energy storage element. In the case of a capacitor, we know that the current relates to the capacitance times the derivative of the voltage. We want this derivative to be a finite, well-defined value. If we have sudden changes in the voltage, this derivative will become infinite, and the capacitor will try to draw infinite current, which of course is not possible. So this derivative must be finite, and hence the logic for having the fact that V of 0 plus must equal V of 0 minus. But we just said that V of 0 minus was equal to 0. So therefore, the value of the voltage immediately after the switch changes position must, at least for an instant, remain at 0 volts. Given that there's no voltage drop over the capacitor, we can then go and use KVL to figure out what the current going through the capacitor should be. So IC at 0 plus is simply going to be 400 volts divided by 100 K, which should give us 4 milliamps. These are our initial conditions for the capacitor current and the capacitor voltage. The next important parameter that we need to know is what the rate of charging is. This is given to us by the time constant tau, which you might remember for capacitive circuits, we had derived that the time constant was equal to the Thevenin resistance seen by the capacitor times the value of the capacitance. How can we calculate the Thevenin resistance seen by the capacitor? Well, the easiest way would be to use the test volt method. In the test volt method, what do we think? We take the endpoints of the capacitor, the nodes, take out the capacitor, replace it with a test voltage source, and turn off all of the independent sources. Now, if we do that, then what can we find? We can find that there is only a 100 k ohm resistance that goes between the endpoints of the capacitor. So our Thevenin must be equal to 100 k, which we have to then multiply with the value of the capacitor, which is 0.1 microfarad. And this, I believe, will give us a time constant of 10 milliseconds. The next thing that we need, the final thing that we need to figure out to be able to actually write the equation of the voltage and the capacitance over this interval is the final value of the circuit. So initially, when we're thinking about the problem, let's forget about for a moment that the switch is going to eventually change at 15 milliseconds. And assuming that we were in position B forever, let's calculate what the final value would be. So final value at position B, assuming a long time has passed. And I'll come in a moment to quantifying what I mean by a long time. So when we're in this position that a long time has passed, we're assuming that all derivatives are equal to 0. Therefore, the capacitor value, you just use the symbol infinity to indicate that a long time has passed. So the capacitor current after a long time is just going to be the capacitor voltage times the derivative, but we're assuming that there are no changes, so this derivative is 0, meaning that the capacitor current has to be 0, which means that the capacitor behaves like an open circuit. When the capacitor behaves like an open circuit, then there's going to be no voltage drop across the resistance, and the capacitor voltage after a long time is just going to be equal to whatever the source voltage was, which is going to be 400 volts. So we can start kind of thinking about how we can draw out what our solutions to the problems are. Let's set up two axes, one for the capacitor voltage and one for the capacitor current, which we're going to kind of draw through. We know that we initially start out at 0. What is the final value of the capacitor current? Well, we said that it had to be 0 because it behaved like an open circuit after a long time. What about the capacitor voltage? Well, we said that it had to be 400 volts. So let's draw kind of this asymptotic limit. We know that over the first interval that we're thinking of right now, our time constant is 10 milliseconds. So if I can just kind of draw out a scaled axis here, where each one of these ticks corresponds to 10 milliseconds, we have 1, 2, 3, 4, 5. This would be 50 milliseconds. We know that if everything continued without having any switch changes, after a long time, we would reach 400 volts. What is a long time? Well, we define a long time as being 5 tau. If tau is 50 milliseconds, this means that if tau is 10 milliseconds, this means that a long time has passed after 50 milliseconds. So I could kind of draw roughly what this, I'm just going to do this in a thin kind of black line where it reached 0 at about 50 milliseconds. The problem, of course, is that we do have some switching behavior, right? At 15 milliseconds, this switch is going to kick into effect. And what is going to happen? Well, the voltage is not going to be able to continue to increase along this same trajectory. Whatever the value of the voltage increase was at 15 milliseconds, it's going to stop there. So we've only really calculated this red portion of the curve so far. And we need to calculate what this intermediate value is so that we can use that as initial conditions for calculating the next stage of the problem. What happens to the current? Well, at t equals 0 plus, we found that the current went up to 4 milliamps. So it's okay for the capacitor current to jump. So we have this kind of immediate rise here. And using the same scale right now, we know that eventually this has to decay down to 0. But as with the first case, there's the switch that kicks in at 15. milliseconds, and it's only going to be able to drop to some intermediate value, which we are going to need to calculate what that is. So how can we calculate now what these values are? To do that, we need to actually write what the equations of the capacitor current and voltage are when the switch is connected to position B. So let's go ahead and do that. The general format, what we given our previous derivations, the general format for any kind of current or voltage variable is that you have the initial value, so let's write V of 0, minus the final value, which is the V infinity we calculated, times e to the minus t divided by tau, plus whatever the final value is. And the same format holds true for the current as well. If we substitute the values for V of t, we know our initial value is 400. I'm sorry, I misspoke. Our initial value is 0. So we have 0 minus the final value, which is 400, times e to the minus t divided by tau, which is 10 milliseconds, plus the final value, which is 400. And we can write that even more simply as just 400, 1 minus e to the minus 100t in volts. And so if I want to now find what the value of the voltage is at just before the switch changes positions again from at 15 milliseconds, I can just substitute into this equation. So V of 15 milliseconds is just going to be 400 times 1 minus e to the minus 15 divided by 10, which if you punch it through a calculator, I got approximately 310 volts. What happens to the capacitor current at this time? Well, to be able to see what happens to the capacitor current, we need to go back to and write our equation for the capacitor current in general. So for the capacitor current, we know that it's the initial value, which in this case is 4 milliamps, minus the final value, which was 0, times e to the minus t divided by tau, which we found was just t divided by 10 milliseconds, which is minus 100t, plus the final value, which is 0. So we're left with just this. And you can then go through and calculate what IC of 15 milliseconds would be, which would be 4 milliamps times e to the minus 1.5. I actually didn't go through and calculate a numerical value for that. So we'll just leave this in this form for now and use it as is. So this tells us now what these intermediate values are. If we go back to our plot, this is going to be 4 milliamps times e to the minus 1.5 amps. And this is going to be 310 volts. These intermediate values are now the initial conditions for kind of a new set of calculations that considers what happens when the switch changes from B to C. So another way of thinking about this is that these values here are telling us what V of 15 minus are, and this would be IC of 15 minus. And now if we want to see what happens in the next step, we have to calculate what these new values are going to be instantaneously after the switch changes position now from B to C. So let's plot what the circuit looks like at t equals 15 plus. At t equals 15 plus, we have a 50K resistor, which is just connected to our capacitor. By continuity, we know that V of 15 plus must be equal to V of 15 minus, which we calculated as being 310 volts. Note there is no continuity constraint on the capacitor current, so we must label this as something else, IC of 15 plus. And we can calculate what IC of 15 plus is by just using Kirchhoff's voltage law on the circuit, given the constraints that we've had. So, using Ohm's law, we can find what this current is, the black arrow as I've drawn it. We can find what that arrow is using Ohm's law. Note that the direction of this black current is reverse the direction that my IC has been defined. So I can just write IC of 15 plus as being minus 310 volts divided by 50K, whatever that might be. It looks like that's something which is around minus 6 milliamps. So I'm just going to approximate and go with it for the time being. So we can update our plot slightly to think about what happens, because now we know that the value of the current is going to jump from 4 to minus 6. I'm sorry that this plot is not quite to scale, but just go with me for the moment. Let me kind of relabel this in a more convenient position. So this is going to jump down to this value here of minus 6 milliamps. The capacitor voltage is going to stay where it is because we have continuity on the capacitor voltage. The next thing that we have to consider is what the time constant is going to be like. So to figure out the time constant, again, you have to consider what the capacitor is connected to. And in this case, we're only left with a resistor and a capacitor. So by observation, we can see that at position C, the time constant is going to be 50 kilo ohms times the value of the capacitor, which was 0.1 microfarad. So let's make sure we keep in our units here. And if you multiply that out, you'll get that the new time constant is 5 milliseconds. Okay. So what does this now tell us about how rapidly we're going to discharge? We can calculate what a long time in position C is. That's just going to be, again, 5 tau, but it's now going to be 5 times 5 milliseconds, which is 25 milliseconds. So going back to our plot, what that tells us is that 25 milliseconds later, all of the final values need to have been reached. So if we add 25 to here, we can see that we must reach our final value at 40 milliseconds, which is here. What remains to be done is we just need to figure out what that final value actually is. So now let's draw what the circuit looks like after a long time has passed. So at t equals affinity, but now we're in position C when we're thinking about this. And again, it's just going to be this resistor connected to the capacitor. But after a long time has passed, the capacitor current must go to 0 because capacitors look like open circuits when they're in steady state. And we have some final value on the capacitor voltage. But note that since there's no current going through the capacitor, by Kirchhoff's voltage law, we can find that V of infinity also must equal 0 volts. So in the end, both of these two curves are going to trend down to 0, but they're going to trend down a bit faster than before. Note that there's a time constant of 5 milliseconds, so if I were to use the asymptote idea that I taught to you before about the slope, we would draw kind of a more steeper drop-off where it ended. Like here, it reached its final value at 40 milliseconds. And here we can apply the similar logic and draw it like this. Okay. So this gives us our final value. The last thing that we have to do is we have to write the equations for this entire period. So the way that we would go about doing this is we would open up a curly brackets, which would allow us to define it for all intervals. So let's first write what V of t would be. V of t is going to be 0 for t less than 0. It's going to be 400, 1 minus e to the minus 100 t volts for between 0 and 15 microseconds. And it's just going to have a value of the initial value, which is now 310, minus the final value, which is 0, times e to the minus t divided by tau, which was minus 100t, plus the final value, which was 0 volts. And this is for t greater than or equal to now 15 milliseconds. We can write a similar kind of expression for the capacitor current. So again, in the initial interval, it's going to have a value of 0. What is the capacitor current doing over the initial period? Well, again, let's look at the initial value. In this case, it's going to be 4 milliamps minus the final value, which when in position B, it is 0, Okay, so this is an important point. When we're writing the equation, we're not really considering the switching at this point. Go back here. If it would have stayed in position B, what was the final value going to be? It was going to be 0. So when we're writing the equation, we're using the ultimate final value, not the interrupted value, if you will. So this is going to be 4 milliamps minus 0 times e to the minus 100t plus the final value, which is again 0, but now this is in amps, and this is between 0 to t and 15 milliseconds. And then afterwards, we have the same consideration now. What is the initial value? It's minus 6 milliamps times, minus the final value, which in this case is again 0, but in this case, since it stays in position C, it actually does reach its final value, minus e to the t divided by tau. I just realized that in my writing of the equations above, I used the incorrect value of tau in the second case. In this case, tau was 10 milliseconds, and in this case, tau was 5 milliseconds. So this should have been minus 200t. My apologies for the arithmetic error. I did it correctly here. This is e to the minus 200t. Again, the final value is 0, so it ends here, and this is what the capacitor current would be for t greater than 15 milliseconds. Okay, so you can see that there's a number of important considerations. The main 3 things that you need to calculate over every interval is the initial value, the final value, and the time constant. You write the equations as though there were no switchings and it just stayed in that position forever. But in the cases where you do have a switch which interrupts it, notice how that is taken into account by these updated initial conditions when we're starting the second interval. One final note that I need to make to fully write these equations in a correct fashion. Note that when I'm considering t in this equation, I'm actually considering how the time is changing since the changing of the switch. In this case, since the switch changes at 15 milliseconds, to truly write this equation correctly, what I would need to do is write t minus 15 milliseconds here to just adjust the time to be on the correct scale. Another way of thinking about it is that you can kind of reset the time axis and think of this as minus 200 t prime, and then later on calculate that t prime, your secondary time axis, is just shifted relative to your global time variable by 15 milliseconds. But when you're actually writing the equations, you need to make sure that you account for the shift that incurs due to your next switching time. So I think now we have correctly mathematically represented the voltage, the capacitor voltage and the capacitor current for all values of time. If you have any questions, please contact me and I'd be glad to upload any kinds of explanations either on a discussion board or in another supplemental video. Otherwise, I hope you all have a good day. Take care and see you all later.